This video is sponsored by Blinkist, more on that later. This is part 7 of openDog version 2. We've had a bit of a break from the series while I did a big build for a brand, so don't forget to check that out. And also looked at autonomous mapping and navigation with a robot I built running ROS. And of course all of those features are going to work their way into robot dogs and other robots in the future. Last time we got it walking, but it was very rudimentary in that basically it's just moving its legs to fixed timers on fixed positions and altering its stride length as I push the remote control sticks around in 3 axes to go and move sideways, back and front, and also rotate. But it worked pretty okay, and inherently this model seems very stable due to its mechanical build and the back drivability of those low reductions we've got on the brushless motors and that 5:1 reduction to the leg joints, so I'm pretty happy with the build overall. Today though, we're going to fix some issues that I had, which I didn't really talk about much in the video and I didn't show you, and then we're going to try and make it work better by using interpolation to drive it slower from A to B in terms of joint positions, so it doesn't have to move its legs so fast. This project is totally open source, and I published all the CAD and code up to part 6 on my GitHub last time, so go and check that out if you want to download it and have a go at building your own, or just use it for inspiration. You can support me through Patreon or YouTube channel membership, and those links are in the description below. And don't forget that I have a merchandise store selling t-shirts and other merchandise with pictures of openDog on and various other things that I've built over the years. So mainly the issues I had, although I didn't show it very much on video, is that the belts sometimes slip. This whole thing is driven with a 5:1 belt reduction straight onto the joint, and it's fine while there's belt tension, and obviously we've got pulleys with lots of teeth, so there's lots of grip, but if there's any skew or sort of forces we're not expecting, then we do get some belt slip. The main problem is the whole thing's printed in PLA because it's very quick to prototype. I didn't want to spend too much money on expensive materials before I knew if it was going to work. So one of the issues is that the motors get quite warm in the knees and actually melting the PLA, and that's causing the motor to skew, and that means that the belt gets loose, and of course there's quite a lot of load on the knee because it's supporting the whole load of the robot, so that belt sometimes slips. And the knock-on impact of that is that the hip motor slips, and that's because the whole frame can skew and those motors don't have any bracing on the end of them, and that's of course an extra force on that motor as soon as the leg gets shorter because the knee has slipped. So that causes that to skip. The only belts that don't skip are the shoulder assembly, but those are really, really tight, and they've also got double bracing because I put a bearing in the end of the motor pulley, and that's braced onto a bit of 6mm steel in the sort of parallel assembly of that hip assembly. So those are okay, but we really need to do something about those motors skewing in the knees. But before we look at that, it's time for a quick ad from the video's sponsor, and that is Blinkist. Blinkist takes insights from 3,000 non-fiction books and condenses them down into 15-minute summaries called Blinks. There are many topics that I really like, including AI and robotics, as well as economics and politics. These can be read through and also listened to like an audiobook, which is really good if your time to read books is limited, and of course you can listen to them while you're commuting or doing other activities. Blinkist also has full-length audiobooks on many topics if you want to get into some of the subjects more deeply. Premium members can get special member pricing, which is up to 65% off the normal retail price. Blinkist has over 12 million active users, and you can join them by using my special link. That's blinkist.com/James Bruton. The first 100 people to use the link can get a 7-day free trial. You can cancel at any time, and if you choose to go for premium subscription, then you can get 25% off your membership. So that's blinkist.com/James Bruton, and I'll put that link in the description to this video as well. Yes, I've reprinted the outer leg where the knee motor lives, and these have now got these metal shims in, which are 3mm aluminium, and that should hold the motor nice and stable and also act as a heat sink to dissipate some of that heat. So that means, of course, the motor can't melt into the plastic anymore and skew. So that should work out pretty well. The shoulder motors are okay, and we've got another solution for the hips we'll look at in a minute. So that's the outside of the leg taken off. So obviously the motor would go in there. I don't know if you can just see, actually, this is actually quite melted in. There's a noticeable dip here where the motor has melted into the plastic. So the new one, of course, has that metal plate on, so we shouldn't have too many issues. So I've just got to change all of them, and we should be good to go. So I swapped all of those out for the ones with the metal shims. Not sure how easy it is to see, but all of these are slightly pitted just here where the motor's melted in and squashed the infill. So hopefully it will be much better now. So we've got all those metal shims in there now, and that's feeling much better. All those belts are feeling really much tighter like they are when they were new again. I thought the belts had stretched, but actually it's just the motor's moved. And now it's time to do something about the hips. So I've got these very special pieces here, which are moon-shaped pieces with little pegs in, and those are going to fit on the two rails that are made of carbon fibre in the dog, and they're going to brace that extra motor which moves the hip assembly. So hopefully that's going to keep some more tension on that belt as well. I fitted one of those pieces on each motor, so you should be able to see the motor turning, and this is now bracing that pulley. Now there is a bearing in the end of the pulley, which is the same as on the shoulder axis. It's the same part. So that piece of 6mm steel is rotating a bearing fitted in the end of the pulley, and that double braces the motor on both ends. So now this belt is really much tighter. The frame can't skew, so we can't lose that belt, and everything should be much more sturdy. So now we should power it up and have another test, I think. The only other change I've made since last time is, instead of having a switch that I switched, which made it step on the spot and then move when I move the control sticks around, it now just doesn't do anything until I actually have a non-zero value on the stick. So as I start pushing that stick forward, it should start taking steps, and the more I push it, the bigger the steps get, and it does that in all three axes for going sideways, backwards and forwards, and also the yaw move for rotating. And of course all of those still mix together exactly the same as they did, but when I'm not moving, it stands still, and that should conserve power. So it works not too badly, really happy with those hardware upgrades. You'll notice though when it starts and stops, it is a bit wobbly, and that's due to that low reduction that we've got, which is one of the reasons it works as well. So I'd say if you're going to build something like this, probably we need more torque on each of those axes to hold it a bit more stable. You'll notice when it yaws that we do get that funny kind of galloping action. Going forward and back is not too bad, and sideways is not too bad, but the yaw is a bit sketchy. So probably you could upgrade the motors to the 100 kV 9235s, which are only 50% heavier, but have twice as much torque. Of course, you'll need two batteries probably, because it will consume twice as much power. I'm only driving 20 amps into each axis though, so we could increase that, and I feel a bit more confident about that now I've got that double bracing on all of the pulleys and also the metal plates. The other thing is we could make it slightly bigger and do an 8-to-1 reduction instead of 5-to-1. So these are upgrades I'm going to consider in the future. But for now, mainly I'm going to try and slow it down, because we are moving all the joints at full speed, and that doesn't give it very long to take the steps, which may be a reason it's quite wobbly in yaw, to try and get its legs around in 200 milliseconds, which is the time it takes to pick up and put its leg back on the ground again, so 5 steps a second. So we'll try that and see what we can get out of it. I really wanted to check with that belt reduction we've got and the motor power that we can actually take the legs off the ground for longer, or at least 2 legs, and the other 2 would support the dog okay. I've actually upped the current on every axis now to 30 amps. Those metal plates help quite a lot. Those motors don't really get hot at all now in the knees, and the others didn't really anyway, so we're quite happy with 50% more power and of course 50% more torque. All I was doing in that demo though was that I've increased the timers, so basically I've increased the time between positions from 200 milliseconds to 400 milliseconds for each step. So all it's doing is going slower, although the motors are actually moving at the same speed, and given that they've got more torque, they're probably moving slightly faster, which is why it's not very good in yaw, and it's okay in sidestepping, but not really very good there either. And that's mainly because the motors are still moving really fast with the other 2 legs off the ground for longer, so it's got much more time to be unstable. Going forward and backwards seems pretty good, but it's still not perfect. So the next thing is to actually slow down the motions so that we fill that gap properly, and we're actually moving much more slowly in yaw and moving more slowly when we sidestep and walk backwards and forwards. So to discuss how we're going to do that for the purposes of this demo, I've slowed the joints right down even more, or at least I've slowed down the timers. So now if I push forward on the stick, we can see those joints moving with big gaps in between them, but you can see the motors are really jerky, and that's because the motors are still moving at full speed. So what we really need to do is slow down all those motions so they fill the gaps between those timers. So if we go back to the kinematic model demo, which is just the inverse kinematics that we put on the robot, and when I move the sticks, it moves in different axes, so twisting this stick will make all the legs longer and shorter and so on, and we've got all those pitch and roll moves, and you'll notice that the joints move very slowly and they go from one position to the other, filling in all the waypoints on the way. So basically what we've got is a kinematic model that means I can move this foot in X, Y and Z coordinates, and it works back all the geometry in the complex geometry for all of those motors so that we get that very good motion. But what's actually happening is I'm moving this stick really slowly, so I'm counting between all of the positions on the way from one waypoint to the other, and it's moving between them rather than just suddenly going from one to the other. The solution to this isn't just as simple as slowing all the motors down. If we did that by just capping the top speed in the O drive, then not all of those joints would get to their position at the same time, because some don't have to move as far for particular moves, and then the foot wouldn't arrive in the right place at the right time. So what we need to do is slow it down before we put it into the inverse kinematic model. And I'm doing that by using the Arduino ramp library, which will smoothly count from one point to the other over a set period of time, and everything's good. So we've got this still running quite slow, but now if I push forward on the stick, you should be able to see that those joints are moving a pretty rudimentary triangle, but they are moving very slowly and interpolating between all the positions on the way. We've got the nice graph there. If I go and turn more axes, we can see those nice triangular shapes and that nice smooth ramp. And the ramp library will actually do other shapes as well, so we could go and ease in and ease out and do various other types of curves. But for now, that's pretty good. There's only one small caveat, which is of course that if the joints move slowly from position to position, then the leg is off the ground for longer because it picks up at the same time, takes some time to get up, but instead of snapping back to the ground, it takes some time to get there. So essentially we need to speed those timers up again, but interpolate putting that leg back down on the ground so the time off the ground is the same. And at the moment we don't have any method of balancing on 2 legs, so we can't have the legs off the ground for too long because it will just fall over diagonally into the direction of the legs that are off the ground. But let's speed this back up again and give it a go and see if it fixes yaw and all those other problems. As you can see, the yaw motion is amazing compared to how it was. It's better than it's ever been. There's still a little hop in there now and again if I take steps that are too big, but that interpolation's really made a difference and it's much smoother and more consistent. I can actually take quite big steps. I think that's fast enough rotation for anybody. As a result of both the interpolation and fixing yaw, which was mainly because of the interpolation as well, that yaw mixes much better with the other axes, and that makes the robot much more manoeuvrable. Sidestepping is much better, and so is walking straight and yawing at the same time, so it can walk pretty much like a dog now and turn as it goes without too many problems. As long as I don't try and move too many axes at once, of course we are moving the legs quite quickly, then we're still alright. So you can see the odd little hop if I do something too outlandish, but on the whole it's much more manoeuvrable and I'm really happy with the way that it's working. So I did do a dirty hack to the yaw when walking forward and backwards, and I'll talk about that in a moment, but yaw with sidestepping is just mixing those axes as they come. But I'm really happy with the way yaw works. If it does get its legs caught and do a funny little hop, it recovers a lot quicker just because all those motions are much smoother instead of jerking the legs at full speed and knocking it off balance. I mentioned there was a dirty hack there when I'm walking forward and yawing, and that is that I'm only yawing half the robot. So when it's walking forward, it's only yawing the back legs, so it's sort of drifting. When it walks the other way, then it only yaws the front legs. So otherwise I found that it turned too tightly pretty much, and that meant as it was walking along and it started to turn, it would fall outwards and the outside legs would sort of fall inwards and it would roll over. So I'm basically only yawing half the robot. What we really need is some dynamics that cause it to kind of translate over into the turn as it goes, or roll over to try and keep its centre of gravity over the legs. But for now that's just a dirty hack in the code that sets the yaw to 0 for the back legs when it's walking backwards, and that's pretty much all it does. Apart from that, everything is just the axes mixed through that kinematic model that I did, so walking sideways and yawing is perfectly good because the robot's longer presumably, so it's much more braced end to end when it's moving in that axis. So pretty happy with how that's turned out. Obviously the gait is really rudimentary, there's no other waypoints there, so we are just moving in a triangle, but we're doing it by moving between the positions slowly instead of snapping between them, and that's made a massive difference. So I'm really happy with that. There's a few other improvements though, which I'll quickly discuss, and all the CAD and code will be published and it's on GitHub. One really simple addition is this tie bar, which is zip tied onto both ends. It's a bit of PLA, and all that does is holds these pieces of the robot together to stop them slipping. All of these sections are of course mounted on this carbon fibre tube that's smooth and glossy, and that means sometimes they sort of slide, particularly with the force on the leg. So what I found was these hip sections were basically moving and sort of jostling up and down and making a banging sound on each end. So that tie bar just holds it together and stops it slipping, and that's about it. Ideally we need to redesign all of this body really, so that these pieces are one piece instead of lots of sections, make them much lighter, probably make them bigger to allow a bigger belt reduction, and there's lots of improvements we could do in another version. But for now that little tie bar holds it together. I've also made various calibration blocks, and those fit just in here, so that you can calibrate the legs to get them to exactly 45 degrees, and that's quite important for the initial setup and the offsets that are in the code. There's also one for the knee that goes in here, and that means it's much easier to sort out when the joints are in the right position for the setup. So I've put these blocks in the CAD as well, so those are all going to be published. It's amazing what a couple of hardware upgrades and a little bit of software can do to make something work much better. I've mentioned other hardware upgrades throughout the video, like bigger motors, better belt reduction and so on, but I'm not going to be building openDog 3 just yet. We're going to carry on with this one because it's looking pretty good and I'm pretty happy with it. Obviously it's not dynamic at all at the moment. We're not using the inertial measurement unit that's fitted in there, and we're not doing anything about reading the joint forces that I discussed in previous videos. So the next thing would be to try and make it a little bit more dynamic, perhaps reading the force with the ground so it can walk on uneven ground, and using the IMU to adjust it so that it can walk up hills and keep its centre of gravity over the legs. That's something that's going to come up in future videos. Also mentioned navigation with ROS. That's something I'd like to do with this robot. It's still a bit jumpy for the laser at the moment, but if we can improve that gait with more waypoints, perhaps that will be possible as well. So there's definitely going to be more updates in this series, although I'm going to be building some other robots that do mapping and navigation so I can get stuck into ROS a bit better, and I've done a few videos on that already you can check out in my channel. So for now, this is all going to be published, as I say. If you'd like to support me through Patreon or YouTube channel membership, then those links are in the description below. That's all for now.